Hi everyone, welcome back. Today we're exploring a new data structure called heaps. And heaps are commonly used in an abstract data structure called a priority queue. As its name suggests, in a priority queue, the items that are in higher priority are dequeued first. So one very common use case for heaps are, for example, to organize numbers such that you always have the smaller number at the top of the heap. And the idea is, if you have heaps like this, for example, a minimum heap of numbers, you're able to support finding the minimum number inside this heap using the top operation in this case. And in this case, this would be O1. If you wish to insert something into the minimum heap, it is very efficient as well. So in this case, insert would be O log base 2n. And if you want to pop something from the minimum heap, in other words, you want to take the smallest number from the minimum heap and remove it, in this case, pop would also take O log base 2n time. So because of that, the minimum heap is commonly used as a data structure to solve multiple technical interview questions. One very famous technical interview question that uses the priority queue is finding the median of data stream. I would link that to a separate video, but on top of that, you will also encounter that in pathfinding algorithms such as the Dijkstra's algorithm. And for our viewers who are interested in how Google Maps work, like that is usually a variant of Dijkstra's algorithm on top of that with additional optimizations. So what I'm trying to say is understanding heaps is important, especially because it's used everywhere. And if you are to do your best to find a position in software engineering or in tech, chances are you will encounter this data structure as well. So for today, we'll be exploring the fundamentals of what makes a max or a min heap, along with the properties of a max and a min heap. We will also show how we can express this heap in a single array using formulas to find what is the parent, the child, and stuff like that. And we also cover how do we insert an item into this max or min heap. In the subsequent videos, we'll be exploring how do we remove an item from the heap, as well as how to heapify a list to become a max or a min heap. So with that, let's get started. So let's go down to a fresh page over here and let's talk in the context of implementing a min heap. One way to implement a minimum heap is by using something called a binary heap in this case. So binary heap. And like its name suggests, this binary over here is a hint to binary trees. And binary trees are data structures, like its name suggests, it looks like a tree, it has branches and stuff. And binary trees consist of nodes like this, and each of these nodes can have up to 2 children. So it looks something like this. It has a left child as well as a right child. In the context of a minimum heap, this binary tree here would have some properties to them. The first property is that each node would have at most 2 children. So each up to 2 children. The second property is that this binary tree must be complete. You must fill up all the nodes at the front before you can start to fill up the nodes at the back. And spoiler alert, we would normally fill up the nodes from a level fashion like this, and we will fill up the nodes on the left before we fill up the right first. So if you try to add on a node like this is not valid because you are expected to populate the nodes on the left first. So we will go through that in a bit. So second thing is tree is complete. And the final one in this case is the property itself that makes that heap a minimum heap or a maximum heap. In the context of a minimum heap, in this case, the number at the parent, let's say parent has a number 7 over here, and it has number 13 and 15 in the children. In this case, this would be a minimum heap because the parent has a value smaller than both of his children. But if you're talking about a maximum heap in this case, then that's the opposite. You would have a number that is larger than the 2 children over here. And the operations of inserting a value and popping a value must ensure that this property is true for all subtrees inside this binary tree. So in this case, FYI, you can take this as a subtree and you can also take this as a subtree. And similarly, if it has children, the properties must be true for these subtrees as well. So yeah, that's pretty much it. So let's go back to the context of a minimum heap in this case. So let's set this to a number that is smaller than both of its children. And the third property is parent value must be less or equals to both child values, because this is a minimum heap. So this is pretty much the essence of binary heaps. So on top of that, we can also express this binary tree as an array. So let's take this tree over here and let's move it down here. And let's try to express this binary tree as an array. So I guess, okay, let me shift this down even further so that we have more space over here. And let's add on additional nodes. So let's say you have 20 like this. And now next question might be, how do we express this in an array-like fashion? So let's say we have an array that has up to 10 positions. 1, 2, 3, 4, 5, 6, 7, 8. 8 is fine. Okay, so we have 10, 13, 15, and 20. And as you might notice, as we discussed earlier, we would populate the numbers in a level-like fashion. And the nodes that are on the left side gets populated in the list first. And you can see that all numbers are filled up at the front. So in this case, we have a complete binary tree like this. Your next question might be, okay, then how do we... Oh, my bad. Okay, how do we... Okay, let me go back to this page here. Okay, how do we get the left and the right child index of a given number? So for example, let's say you're looking at the node 10 over here, and 10 in this case, the index is 0. How would we get the index of 13 and 15 in this array-like fashion over here? So we have a couple of formulas, fortunately. So if you want to get the left child index, this would be equals to 2 multiplied by I plus 1, where I is the index of the parent node you're trying to get it for. So let's do a simple example in this case. So now we can see that the index here is 1, 2, 3, like this. And if we plug in I equals to 0, we are getting the left child index of 10 after all. We will get 2 multiplied by 0 plus 1, and that gives us 1. And you can see that this corresponds with the left child of 10, which is 13 over here. Then for the right child, this would be 2 multiplied by I plus 2. And if we plug in I equals to 0, we will get 2 multiplied by 0 plus 2, giving us 2. And this corresponds with the index at the number 15. And these are pretty much the formulas. So the next formula is, how do we get, for a given node, how do we get the index of its parent? So for example, let's take a look at 13 and 15. How could we get the parent index for 13 and 15? So there is a formula for that as well. So the parent index will be equals to I minus 1 floor division 2. Okay, I guess I should make it clearer like this. So if we plug in I equals to 1, and I equals to 1 in this case refers to the number 13 in this case, the expected number is 0. So if we do 1 minus 1 floor division 2, we get 0. And if we do I equals to 2, which is the right child of 10, we would also expect an answer 0 in this case. So we will get 2 minus 1, floor division 2. 1 floor division 2 will give us 0. So we end up with the right answer of 0 in this case. So this is pretty much the essence of how we would represent a minimum heap in an array-like fashion, where we populate every single item into the array from left to right, level order. And we also went through the 3 formulas that allow us to still maintain this heap-like property by knowing how do we get the left child, the right child, and the parent index of a given node in this list. So now that we got this down, the next chain of thought might be, okay, now that we know how to express this binary heap as an array, how do we insert an element into this array then? So let's take this whole diagram over here and shift it down and put it here. Let's say we want to add in an additional number like this. So let's add in 1 in this case. So if we want to add in 1 into this binary heap over here, notice that the first step would be to add this 1 at the back of the array. And as you might see, this is the pictorial representation of this, just to reiterate again. But you might see that we have violated the property of binary heaps in this case. So you can see that the parent over here has a larger value than its child. So one way we can fix this is by implementing an operation called heapifyUp. Oh, oops. Okay, let me draw this. And heapifyUp, as its name suggests, is meant to take the final element that was just inserted and compare it with the parent. And if its value happens to be smaller than the parent, we will swap it with the parent like this. So we would compare 1 against 13. And since 1 in this case is smaller than its parent 13, we will swap them. So now we get 1 and 13 like this. And in this case, we can see that the property is achieved for this smaller subtree over here. So this subtree over here is pretty much a minimum heap right now. But we can see that the property for a minimum heap between this node and this node is not achieved. So we have to fix that. So how do we fix it? We would also recursively check this current node that we are at with its parent as well. So we will continue to do this swap till we reach a node that doesn't have a parent node anymore. So we will compare 1 and 10. In this case, 1 is smaller than 10, so we would swap them. So remove this, and let's put 10 here, and let's put 1 here. And just like this, we have successfully inserted an item at the back of the minimum heap, and we swap them around such that we achieve the minimum heap property even after inserting a number. So after we insert it, we can see that we have okay, I guess I should show the swapping in this case. So initially 1 was at the back, so what we did is we swapped it together with its parent in this case. So 1 in this case, like we'll be swapping with 20, 15, 20, 21. So 1 in this case would swap with 1 in this case. And what we did is we did a second swap between this one and this over here. So we get 1 and 10. And if we check all of the values in the list again, 1, 10, 15, 20, 13, yep, this is achieved. So this is pretty much how we would insert a value inside a minimum heap. So now, at this checkpoint, let's do our best to implement this in multiple languages. Okay, now that we have the algorithm down, let's try to implement this minimum heap together with the insert method to add a value to this minimum heap. The first step will be to define a class called meanHeap. We will define the constructor as well as the insert method. The insert method also has a couple of other helper methods such as heapifyUp, as well as other methods to get the parent index or the child index. But that's a lot of words, so let's get started. The first step, define the minimum heap. And at this point, you might notice that your editor is complaining that it does not match the package. This file does not match the package defined. In this case, this Java file is defined under the heaps folder or package, so let's define package heaps like this. Once we're done, we're ready to define the constructor, public meanHeap. And in this case, this constructor will take in one parameter, which is the maximum capacity. So min int max capacity like this. We will also define three attributes inside this class over here. The first is max capacity itself. So private int max capacity. The second is referring to the integer array, which will represent the heap itself. So in this case, let's call this heap. And finally, the size. So we will be setting these three attributes in the constructor. We would define this max capacity to be the input max capacity. We will initialize the size to be 0. And in this case, this size represents the current size, or rather the number of elements inside this minimum heap. And finally, this .heap will be initialized to be an integer array having the same size as the input max capacity. So just like this. So at this point, we are ready to start implementing the insert method. The insert method would be public void. In this case, it returns void because this insert method is responsible for mutating the state of this heap. To be more specific, it's just going to add one value into this heap, so it doesn't return anything. The first thing before we insert it is to check whether if the current size of the heap is already at max capacity. And if that is the case, we will raise an exception. We could have copied all values in the heap and copy them into a heap of double the size, or rather resize the heap. But for the sake of this demonstration, let's keep it simple and raise an exception. So if this dot size is equals to this dot max capacity, then what we will do is we will just throw a new exception, this new exception object, and let's pass in an error message. Yo, your heap is full. Just like this. And at this point of time, you might notice that Java is complaining, hey man, we are not handling the exception. So you can either choose to have a try catch here, which doesn't really make sense. We want this method to raise an exception, possibly. So we will just put throws exception to make the function signature clear that this method can potentially raise an exception. So now that we are done, if we pass this check on size and max capacity, the next step is to insert this value into the heap. And as we discussed, how we would insert a value is by putting this value at the very back of your heap. So to do that, this .heap, this .size equals to value. Oh yes, of course, I've got to specify the input value over here. And in this case, this works because the previous size prior to inserting this value is pretty much the new index for this value because arrays are 0 indexed. So this works. Then afterwards, we will increment this .size by 1 to officially increase the size of this heap. And afterwards, we will call heapifyUp. So heapifyUp is not implemented yet. We'll be implementing that in a bit. And the purpose of heapifyUp is meant to check the final element that has just been inserted with its parent. And if this new value happens to be smaller than the parent, we will swap them. And we will recursively do this till we either reach the top of the heap or until no swap happens. When that happens, it means that the minimum heap property has been achieved. So at this point of time, let's proceed to implement the heapifyUp method. Notice that in this case, I am making this a private method because this method is meant to be used as an implementation of insert. So in this case, heapifyUp doesn't take in any parameters, and let's get started. The first step would be to get the current index, and this current index should be pointing at the final index in this case. So in current index will be equals to this dot size minus 1 since it is 0 indexed. And the next step would be to check whether if this current index has a parent. So while has parent current index, then what we will do is we will get the current index. So int parent index equals to get parent index of current index. So you might notice that these two methods are not implemented yet. We'll be implementing them in a bit. But the idea is that as long as this current index has a parent, we will proceed to get the parent index. And using this parent index, we can do a comparison. So if compare parent index and current index, or rather if the current value at the parent happens to be more than the current index, then we will perform a swap in this case. So if that happens, then we will do a swap parent index with current index. And what we will do is set the current index to the parent index in preparation for the next iteration. So if the parent element happens to already be smaller than the current index, then we would just return, because we have just achieved the minimum heap property. So as you can see in this implementation, we have abstracted out pretty much 4 methods that we have to implement now. So let's do that. So the first method is has parent. So this checks whether if a given index has a parent index or not. So has parent, and this takes in a current index and it returns something. So in this case, to do that, it will just be get parent index, current index more than or equals to 0. And coming right up, we'll be defining another method which is called get parent index. And this get parent index pretty much returns the parent index of a given index. And as you might remember from the previous demonstration, the formula for getting a parent index is current index minus 1. And we will do a floor division. So math.floorDiff. And floor division in this case takes in 2 parameters. First the numerator followed by the denominator. So just like this is pretty much done. So, oh sorry, the function signature is incorrect. We were supposed to return an integer in this case. Now we are left with 2 more methods to implement, which is compare. And compare in this case gives back a boolean. And if the boolean is true, it means that the minimum property is achieved. So, so now let's say int left index, int right index. So I guess I should make it clearer because this function name is not that clear, but if left index, if value at left index less than value at right index, return true. Yep, so it will just be this dot heap left index less than equals to this dot heap at right index. Sorry, less than or equals to, I guess. It's completely arbitrary in this case, like you can choose to make it, okay, oh sorry, in this case it should be boolean, not bool. And now we have compare in this case. So what this means, pretty much to reiterate again, it means that if this condition is true, it means that the current value in the parent is currently more than the value of the current index, and there should be a swap. And the final method that we're implementing is swap itself. And because we are swapping 2 values in this case, this method doesn't return anything as well. So in this case, to swap, we would set an initial temporary variable to refer to this dot heap at left index. And the reason why is because we are just about to overwrite this heap.left index with this .right index. So we need this temporary variable to store the value of the left index prior to being overwritten. This way, we can set heap right index to be equals to temp. So this is pretty much it for this demonstration. Let's try to use this class to create a minimum heap object. And we will try inserting values in descending order and try to print out the first value inside this minimum heap to be sure that this is implemented correctly. So let's define a main method here, public static void main string args, the famous main method. And what we will do is define a minimum heap, and we will call the constructor to define a new minimum heap object. Of course, in this case, it's complaining because we haven't specified the maximum capacity. Let's define 100 up to 100 elements in this case. Now the next step is to try inserting some values inside this minimum heap. For I equals to 10, I more than equals to 0, I minus minus. We will do minimum heap, insert I, and now, oh, why is it complaining? Oh yes, of course, because this method throws an exception. Java is saying, hey man, you should be handling any possible exceptions in this case. So try catch exception SE. So if it happens, although it shouldn't happen, but okay, in this case, we would do, oh sorry, exception E. Sorry, I came from the land of snakes. Got all my syntax wrong, but system out print line get message. So exception objects have this method get message, and this lets you get the message defined in the exception over here. So that's pretty much it. And after we have inserted this, we want to print out everything that is inside this heap over here. But unfortunately, if you print out this heap, you would get a memory, you get a reference instead. So just to prove that to you, let's try printing out the minimum heaps. I guess this integer array over here. Let's make this public so that we can access it. So min heap dot heap in this case. And unfortunately, if we run this, it's not going to work because this is going to print out the memory reference instead of the heap in an array fashion. So let's do java heap slash min heap dot java. Oh sorry, I need to compile it first. So now it's compiled, java heap slash min heap. You can see that it prints out a cryptic string over here that is not definitely what you want. We want something like an array-like thing where it's some values and a couple of nuns as well. It should look something like this. So to make this object be printed, we can override a method, a standard method automatically defined in min heap called toString. So let's override this public string toString, and this method can be called to get the string representation of this class. So what we can do is define a string builder, and inside this string builder we would iterate through every value inside the heap and add it into this string builder. So for int I equals to 0, I less than this dot size. This by right should be the case, but I will get to it in a bit that we do not want this. We probably want this size -1, but over here in the string builder, we will append I together with a comma like this. But as you might notice, we probably don't want the comma at the very back of the string for the after the final element. So instead of doing this comma appending, we would just do this for all elements except the final element and append I separately over here. Oh yes, of course, we were supposed to get the value of this dot heap. So this dot heap size -1. This is pretty much appending the final element inside the heap inside the string builder. And once we're done with just string builder called toString, and now we would have this helper method to express this heap as a string representation. So let's do minimum heap dot toString now like this, and let's try compiling this code again and run it again. And as you can see now, the heap is the heap currently has 0 at the top of the array, which is what we want. And we can see that 1 has his children 4 and 2, and both of his children are larger than itself. And for 5 over here, it has 2 children, 9 and 6. And in this case, both 9 and 6 are larger than 5. So you can see that the property of minimum heap is achieved, even though we inserted values in descending order. So this is a pretty decent demonstration, I think. I hope this was useful. In the subsequent videos, we'll be focusing on how to implement deletion, popping one value from the minimum heap, and how we ensure that this property of minimum heap is still achieved using heapifyDown. We will also go through heapify, which takes in a single array of elements, and we will make it into a minimum heap or a maximum heap, and how this heapify method is more efficient because it's done in O(n) time instead of n log n. So with that, that's pretty much it, and see you in the next video.